Good morning. Myself, Dr.V.Balasubramanian, Assistant Professor of Physics, School of Basic Engineering and Sciences, PSN College of Engineering and Technology, Tirunelveli. Today, I am going to discuss about the topic photoelectrochemical solar cell, its basics as well as its applications. So, these are all the outline of my presentation. So, why we are moving to solar energy? So there are different kinds of energy resources are available. So here I am going to concentrate on why solar energy is a predominant one when compared to the other available energy resources. Then what is the need for water purifications? Then I can give you an overview of photoelectrochemical solar cell. I will give you the basics and then material requirements. So this table gives, this chart shows the global populations. As we know that the global population tends to be increases with the increase in the years. When the year starts on increases, global population also increases. So we need to concentrate more on the energy aspects. So that's why people nowadays research is moving on various energy resources. Next, let us come to an important point. Here is the criteria for finding out a new energy resource. As I said already, there are different kinds of energy resources are already available. So what are they? They are solar energy, wind energy, hydrothermal energy. Likewise, various energy resources are available. Here I am going to particularly concentrate on the solar energy resource. So what is the advantages of using solar energy and what is the criteria for new energy resource? Let us see. So the first one is it should meet the requirements of mankind in years to come. It should, and the second one, it should be inaccessible, replenishable, non-pollutant, and should be available all over the world freely and should be free from tax. So that is the most important. Here the solar energy is available free of cost. We may not want to pay for it. So most of these energy demands in India can be met by these simple solar systems such as solar photovoltaics, solar cooker, solar hot water system, and then solar dryer, etc. So these are the major criteria for finding out the new energy resource, that is for solar energy. So here are some. Here we are having some both advantages as well as disadvantages. So first, let us look into the demerits, that is disadvantages. So the solar energy, which is intermittent in nature, and the second one is here we have experienced an extra cost and the complexity of storage. But when we look into the positive side of solar energy, our Earth is almost receiving a power of 1.8 into 10 power 11 megawatt, which is several thousand times larger than the total world's energy consumption. So this is an added advantage of solar energy when compared with the other energy resources. Here, our Earth receives almost an energy of 5 kilowatt hour per meter square, which is approximately equal to 4,300 kilocalorie per meter square. So these are all the criteria for new energy resource. So this table gives you the solar spectrum. Our solar spectrum, that is sun's energy, is having different kinds of solar spectrum, so that is different kinds of wavelengths. It is having ultraviolet range, visible, and then infrared. This wavelength range as well as this energy range is tabulated in this figure, in this table. As I told earlier that there are vast number of energies received from the Earth surface. So here the world requirement is, for the total world, the energy consumption is found to be in the range of 4.1 into 10 power 20 joule per year. So that is the advantages of solar energy. Here the solar energy is abundant, but it is dilute. It is available for about 5 hours in India on the average. It consists of a spectrum with maximum number of photons at about 1.5 electron volt, and is spatially as well as temporally variable. So these solar energy can be converted into heat, chemicals, bio and photochemicals, electricity, and etc. So So this is an industrial waste. So why we are seeing this image in this sense means we have taken solar energy. Using that solar energy, we are going to fabricate a semiconducting thin films. That thin films can be used for water purifications. That's as I said in the introduction part, that is the outline of my presentation. We are going to discuss some of its applications. So what I have taken is I am going to take a semiconducting thin film material which is prepared using a chemical method, and this application is studied towards water purifications. So this is the wastewater, industrial waste, industrial outlet mixing into river. The next, water pollution by garbage, and then this is the bed of river covered by water plants. Dyes discharging 50,000 tons per year in waters. So we all know that is it a drinking water? It's not a drinking water. So we are in a state, or people are moving towards finding out clean clean energy resource using solar energy. Using that solar energy, people are moving towards water purification applications. So there is nothing else like it on the earth. So out of 100% water on the earth, 97% is saline water, and 1% is polarized, and the glaciers are plus 2% on the surface water. So out of this 2%, 80% water is polluted due to human activities. So due to the industrial activities and other human activities, we are polluting almost 80% of the water from the earth surface. So this is really a drawback to us. So this figure was estimated by the various agencies, EPA, WHO, ICMR, and NADI, that about 2 million human deaths per year occur due to polluted water. So out of this 2%, 70% is meant for agriculture, 20% is meant for industry, 10% for private households is being utilized. So therefore, purification of water is of paramount importance. So we all know that our technology is developed. So development is must, but we need to concentrate on our environment also. So therefore, purification of water is of paramount importance. So why we have taken water? Water is an indispensable source of life. So what is potable water? It is chemical free, metal free, bacteria free, mineralized, and then purified waters. So that's why we have taken water purification applications using semiconducting thin films. So these are the major technologies used for water purification. The first one is filtrations, that is particle filtration, micro, ultra, nano filtrations. There are various methods are available. The second one, adsorption, that is absorption by activated carbon using organic materials and organics and other chlorine materials. Then the third one is ultraviolet radiation. Ultraviolet radiations, here water purification can be done with the help of microorganisms. And the fourth one, it is distillations using laboratory grade. The fifth one is deionization, that is for using ion exchange. So in alternative to these five major technologies, we have concentrated on photoelectrocatalysis. As I said earlier, here we are using sun energy. So the sun energy is focused on a reactor cell. It consists of a working electrode and then counter electrode. There we have applied a bias, we have applied some voltage. So using that voltage, that semiconductor material is having its own band gap. So when the applied potential exceeds the band gap of the material, so electron volt transfer takes place, and then we get the electrochemical reactions takes place, and then finally we get the purified water. So this figure gives you the energy levels, that is before contact and after contact. So what we are doing is we have taken a semiconductor material. So as we all know that semiconductor is different from conductor as well as insulator. The semiconductor material is having a conduction band and then valence band. So for an N-type semiconductor, the valence band and conduction band, the Fermi energy level always lies close to the conduction band, whereas in the case of a P-type semiconductor, the Fermi energy level always lies close to the valence band. So this is the energy levels that exist before contact as well as after contact. So this slides gives you the band bending diagram at the n-type semiconductor during the electrolyte interface. So what we have done is we have taken a semiconductor material which is immersed in a beaker that consists of an working electrode. We have taken working electrode, semiconductor material is the working electrode, and the counter electrode may be a platinum electrode, and then reference electrode should be Ag, AgCl or some other things. So this figure gives you the schematic diagram of photoelectrochemical solar cells. So here we have taken N-type semiconductor. So the photoelectrochemical solar cell comprises of a photoelectrochemical cell which is having an N-type semiconductor which acts as a working electrode, and then a counter electrode, and then the third one is electrolyte. So as I said already, we have applied a bias. Here a potential is applied which is measured, which is given through the resistance, and the total voltage absorbed from released from the photoelectrochemical solar cell is measured using ammeter. So this figure also shows the schematic diagram of photoelectrochemical solar cells. Here we have taken a valence band and conduction band. As I said, before contact, that is after contact, Fermi energy level is always close to the conduction band. And then here also the electrochemical reactions takes place, that is electrons and holes are produced. So let us validate the same using this animated video. Here a photon, that is light energy, is allowed to fall on the photoelectrode. So when the light energy is allowed to fall on the semiconductor material, here electron are ejected from the surface of the semiconductor and it is moved towards the counter electrode. So this process was repeated when the lights continuously fall onto the semiconductor material. So criteria for the selection of semiconductor photocatalyst. So as I said, semiconductor consists of valence band and then conduction band. In the case of valence band, the valence band always lies below the redox potential of the pollutants. If direct oxidation of pollutants by valence band holes has to be occur, or below the redox potential of the water, indirect oxidation via OH radicals has to be occur. So this is the case for valence band. In the case of conduction band, the conduction band always lies above the redox potential of the oxygen. So this is the main condition. So let me repeat: valence band always lies close to the redox potential of the pollutants, whereas conduction band always lies above the redox potential of the oxygens. And the third point, we need to look into the stability aspect. Here a photocatalyst must be always stable against anodic corrosion. So this is the redox potential of the pollutant. This is the redox potential of the pollutants. This is redox potential of the oxygens. So as I said here, let us cross check the following things. Here also the Fermi energy level lies close to the redox potential of the pollutants as well as redox potential of the oxygen. So this is the simple schematic diagram for selection of semiconductor photocatalyst. So what is catalysis and what is photoelectrocatalysis? There is a slight difference between these two. Photocatalysis is nothing but it is a process involving absorption of photons in a semiconductor followed by generation of charge carriers, that is electrons and holes, or OH radicals produced by them. It oxidizes solutes. Here most of the holes and electrons recombine, thereby limiting their efficiency. So recombination is a major disadvantage in photocatalysis. In the case of photoelectrocatalysis, here enhancement in photocatalysis by applying a potential. Here we can be able to maintain an effective charge separation, increase in efficiency of oxidation at the semiconductor electrolyte interface. So this is the simple difference between these photocatalysis and photoelectrocatalysis. So in photocatalysis, that is nothing. We have not applied any external potential. We have not applied any bias. Whereas in the case of photoelectrocatalysis, we have applied a bias. We have applied a potential. So that is the only difference between these two. This is the overall diagram, that is band edge diagram of various semiconductor materials. Here we have taken gallium arsenide, gallium phosphide, cadmium selenide, cadmium sulfide, zinc oxide, iron oxide, tungsten oxide, tin oxide and titanium oxide. So out of these various class of materials, titanium dioxide and tungsten oxide is found to be mostly stable in anodic correction, and it is found to be stable in long time illumination also. Whereas cadmium sulfide and cadmium selenide, these are found to be unstable, even though the band gap of the material of cadmium sulfide and cadmium selenide is found to be in the range, that is for cadmium selenide it is 1.7 electron volt, for cadmium sulfide it is 2.25 electron volt. Though the band gap of the material is very small, but it is found to be unstable. Whereas in the case of titanium dioxide and tungsten oxides, the band gap is almost higher when compared to the chalcogen materials. That is, TiO2 is band gap of TiO2 is 3.2 electron volt, whereas for tungsten oxide it is 2.6 electron volt. Even though it is having a higher band gap, it is found to be a stable candidate for suitable water splitting. So what we are doing is, we need to do reduction as well as oxidation. So reduction occurs at the conduction band potential. So that is nothing but that conduction band potential is more negative than the potential of reduction reaction. In the case of oxidation, oxidation occurs at valence band. That is, valence band potential is more positive than the potential of oxidation reactions. So we have taken titanium oxide, tungsten oxide. So using titanium oxide, we have modified its morphology. So we all know that titanium dioxide exists in two kinds of phases. It is a rutile phase and anatase phase. Similarly, tungsten oxide is found to be a suitable candidate. So we have taken tungsten oxide. We are also concentrate on ternary copper-based ternary metal oxides, that is copper tungstate, copper niobate. So similar class of materials we are working on towards photoelectrochemical hydrogen generation as well as photoelectrochemical solar cells. Similarly, for chalcogenides, we are working on copper sulfide, copper selenide. Likewise, ternary metal oxides, ternary metal chalcogenides, we are also working on copper bismuth sulfide. So these are all the various class of materials. So this is the energy level diagram for various semiconductors, indicating the energy positions of valence band and conduction band edges in aqueous medium at pH is equal to 1. Next, let us see the requirements of a photoelectrode. So what is the main requirement for a material to be act as a photoelectrode? So the first one is, it should have an optimum band gap energy. So the band gap energy of the semiconductor material, or it may be called as a photoelectrode, whether it may be a photoanode or photocathode. So a photoelectrode or a semiconductor material should have the optimum band gap energy, and it is found to be in the range of 1.4 to 1.6 electron volt to absorb the solar spectrum. So this is the first condition. The second condition, it should be stable in electrolyte and it should not decompose during illuminations. So because we are we are doing long-term illumination process, we have taken one sun illumination condition. That is, one sun is nothing but 100 milliwatt per centimeter square. So such a long-term illuminations can be processed. So during that process, our material should not decompose or it should not peel off from the electrolytes. So that is also very important. And the third one, it should be of direct band gap type. So direct band gap type, in the sense we are going to predict this with the help of optical absorption. So absorption coefficient is found to be in the range of 10 power 4 to 10 power 5 centimeter inverse. Then the charge carriers. The charge carriers in the material should have high mobility and lifetime. So the next one is thickness of the material. So thickness of the material should be enough to absorb all the incident light. We are using solar spectrum. Solar spectrum consists of UV radiation, infrared, visible. So that thickness of the material should be optimized in order to absorb all the range of incident lights. And the last one is cost of the semiconductor material, and then the manufacturing process should be low. So these are all the main requirements of a photoelectrode. Next one is requirements of a electrolyte. So since photoelectrochemical solar cell involves the it is similar to a photoelectrocatalytic process. As I said, it is having definitely it is having an electrolyte and semiconductor the electrode materials. So what are the requirements of the electrolyte means it should possess oxidation reduction reactions should occur at appropriate semiconductor band edges. So that is the first condition. Then it should have a charge transfer rate of oxidized and reduced species should be high. And the third one, oxidized, reduced and solvent components should have a photo and thermal stability. And the fourth one, it should be non-corrosive to electrodes, because if you are working with stainless steel material, it is possible to occur corrosions. So in order to avoid this, people are working with some conducting materials like FTO, ITO and similar materials are there, molybdenum coated glass substrates. There are different kinds of conducting glass substrates are there. So people are using the glass substrates. The fourth one is minimum light absorption should occur in the electrolyte. And the fifth one is ionic conductance of the electrolyte should permit negligible ohmic losses. And the last one is toxicity, reactivity and cost should be preferably low. So these are the main requirements of the electrolyte. Then requirements of the counter electrode. It should have a low over potential for the reduction reaction, large area to avoid concentration polarization, and it should be chemically inert. So these are the requirements of the counter electrode. So before I am going to conclude the entire topic, so we are this research is this photoelectrochemical solar cells particularly applied towards different kinds of applications. The most important one is water purifications. So in order to purify a water, we are going to synthesize a material, that is semiconductor material, using a physical method or chemical method. It may be of any kinds of method that is available during the synthesis process. So after the synthesis process, we have studied its structural characteristics using X-ray diffraction, FTIR, Fourier transform infrared spectrometer, and their morphological characteristics are analyzed with the help of a scanning electron microscope, and the elemental composition is confirmed using EDX spectra. Then it is applied towards water purification technology using a photoelectrochemical solar cell process. So these are all the overview of photoelectrochemical solar cells, and this is the basics and as well as its applications. Thank you.